we've talked about how to do inference for one mean. We've talked about how to do inferences for two means. Well, what about inferences for three or more means? And that's what our next section talks about. This next section is called an introduction to ANOVA. ANOVA stands for analysis of variance. And you might be wondering, well, that's kind of weird because you just said that we're looking at how to do inferences for multiple means, but yet this is called analysis of variance. We'll eventually talk about why it's called analysis of variance in our notes. Okay, so again, we have this diagram that we've been talking about all semester long here, where now we potentially have multiple populations, and we're going to take samples from multiple populations, and we like to do inferences for multiple means. Specifically, we would like to be able to actually compare means. Is mu1 equal to mu2 equal to mu3, and so on? And if they're unequal, where do the differences lie? Maybe mu1 and mu2 are equal, but mu2 is different from mu3, and mu3 is different from mu1, and so on. So where would something like this be of interest to do inferences for multiple population means? Well, so for example, when I was in grad school, I went to Kansas State University, and wheat is a big thing there. And so one of the projects that I worked on when I was there was to determine, well, among different wheat varieties, which will produce the highest yield of wheat on average. So what we can do is look at, let's say, mu1 might be for the Newton variety. Mu2 might be for the Rough Rider variety. Look at, let's say, a hypothesis test that looks at are the means equal versus one pair of means that's unequal. That's what we do in analysis of variance. Another example would be involving grocery stores to determine, well, which grocery store has the lowest prices on average, Hy-Vee, Walmart, or Super Saver. So in this case, you can think of it as maybe, let's say, having three different population means. And then based upon your analysis, then, of course, you can make a decision of, well, which grocery store might be the most cost-effective to shop at. In the pharmaceutical industry, they use analysis of variance of all the times to determine which type of medical treatment might be the best. So, for example, excuse me, we might want to compare, let's say, three different allergy relief medicines, and which provides, let's say, the highest average relief from the symptoms when they're given to patients. And lastly, a very simple one, let's say that we're looking at three different types of fertilizer applied to a specific variety of wheat, which produces the highest yield on average for the actual wheat itself after the fertilizer is applied. So in each example, we're looking at a hypothesis test that you could write out in a very general form such as this. Mu1 is equal to mu2 is equal to mu3, all the way down to, let's say, we have t different population means that we're interested in. So the null hypothesis is that all the means are equal. The alternative hypothesis is at least one pair of means are not equal. So it only takes one pair, two of these means, to be unequal for the entire null hypothesis to be incorrect. So again, this procedure, the statistical procedure that's used to do a hypothesis test like this and actually to continue doing some other stuff involving these means is called analysis of variance. And this name again might sound strange, but how we can actually determine which means are unequal to one another comes down to looking at different measures of variability. And we've talked about one with respect to the sample variance, where we look at how far is our observed value from the sample mean. But there's other measures of variance that are just like that could be used as well. And then when we compare the different variances, then that will tell us which means might be different. Okay. Also, we'll, again, as we've done before, we'll try to relate what we're doing in a mathematical or statistical concept to plots, so that it helps us to make sense of what's going on. Now, there's a lot of terminology that comes with analysis of variance. Now, Now, one of the very first places where analysis of variance was needed or used was with respect to agricultural applications. And that's why, for example, most universities that have a significant agricultural component also have a Department of Statistics associated with it. And in fact, usually that Department of Statistics was started to help out the people in ag for how to set up their experiments, how to analyze their experiments. So again, because of this, then a lot of the terminology that we use here actually comes from agricultural applications. Okay, some very basic terminology first of all. The process for collecting the sample data is simply called an experiment. So, if I'm interested in looking at the different wheat varieties, which has the highest yield, I perform an experiment. So I actually do the planting, collect the yield information. That's my experiment. Now, the plan for collecting the data is called the design of the experiment. So, for example, should I, let's say, apply different varieties to one piece of land versus another piece of land, and so on. And for this reason, then, experimental design, then, is a very important component of statistics. In fact, many of you will take a course called experimental design sometime in your graduate school experience for that reason. So a lot of the stuff that we're doing right now is extended greatly in a second course. Okay, so let's take a look at some examples. So with respect to that grocery store example where we want to determine which grocery stores are the grocery store prices on average the same, or are they different? What we could do is randomly select 10 different items that would be sampled at each store. That would be our design. And the key reason why we want to design it in that way is because by sampling the same items at each store, let's say maybe a box of Wheaties cereal, it allows us to make direct comparisons on exactly the same item at each store. And the reasons behind we would want to do that are exactly the same as what we saw previously when we were doing hypothesis tests for µ of D, when we had this paired data. So the experiment then in this particular situation would be going out and collecting the prices of the items. With respect to the fertilizer example, what we could do is randomly select some field locations where each type of fertilizer is being used. That's the design. And then the experiment is planting the wheat and obtaining the yield for the particular field location. Okay. Now, the variable that we actually measure in this experiment is called the response variable. And the reason why it's called a response variable can be seen from this second example. So I'm going to apply fertilizer to some land. Also, I'll plant some wheat. My response variable is the yield. In other words, we're interested in how the wheat responds to the fertilizer. Thus, yield is my response variable. In the grocery store example, our response variable simply would be prices. Now, the variables that might be related to the response are called factors. In other words, we have the different grocery stores. A factor is the actual grocery store chain. So Walmart, Super Saver, Hy-Vee, or whatever grocery stores you're looking at. With respect to fertilizer, the factor would be the fertilizer type. We have A, B, and C. Now, that A, B, and C is what's called factor levels. So it's the different possibilities of that corresponding factor. Now, these levels can be equated to different populations when being compared. So, for example, two factor levels that we would be examining we might be interested in then comparing the mean for factor level 1 to the mean for factor level 2 by simply subtracting the two. So again, the factor levels are particular parts of that factor. Now, a treatment is a particular combination of levels of factors. Now, in our class, we're only going to be talking about essentially one factor at a time, such as grocery store chain or wheat variety and so on. But in more advanced classes, like a course on experimental design, you might have 2, 3, 4, even more factors that you are actually looking at. And a treatment in that particular setting is a combination of factor levels from the different factors. So for example, which variety of hard red winter wheat and fertilizer provides the highest yield on average? One treatment would be, let's say, if we apply to a particular plot of land fertilizer A, and I'm also going to plant the Newton variety there. That would be one treatment. So the name treatment then comes about from items being treated with a combination of factor levels, which makes more sense typically in an agricultural setting. And we also can have what's called an experimental unit. The experimental unit is the object in which treatment is being applied. So with respect to the fertilizer example, our piece of land then essentially is the experimental unit. That's what we're going to measure. We're going to find the, let's say, the yield for that piece of land. So here's a more of a breakdown. Maybe at some kind of agricultural experimental station, we have a piece of land. We divide it up into 12 different parts, where in each part we apply one of the particular fertilizers. Each of these squares then will give us a yield, and that will be our, so that essentially then means our experimental unit is one of these pieces of land, and we measure our response variable, which is yield. For the grocery store example, the experimental unit is the actual item at the actual grocery store. That's what we're going to observe what their price is. So that was a very brief introduction to a lot of terminology. Obviously, the terminology is going to be new to many of you. And what we will do now for the rest of this section is apply this terminology so that we can actually analyze some data with this method called analysis of variance.